Hello guys, so today we're going to be looking at this one question here, and we'll be doing it as a worked example. So I'll just read it out quickly. A pair of students in the lab wanted to determine the enthalpy change of neutralization between HCl and NaOH. In order to do this, they took 50 milliliters of 2 molar NaOH and 51 mils of 2 molar HCl. They mixed the two solutions together in a coffee cup calorimeter using and they recorded data using a temperature probe connected to a data logger. The graphs they obtained are shown below. Here's the graph they obtained. And using this data to determine the enthalpy change of reaction, assume the specific heat capacity of water is 4.18 joules per gram degree Kelvin. And here's the data they collected. Pause the video if you want to try the question out yourself now, and come back for the solution. Right, so I assume you're back. So the first thing I always like to note is enthalpy changes. So let me just delta H is equal to negative Q reaction over N lim over the number of limiting moles. Now, there's a reason why this is the case using experimental data, and there's some logic behind this formula. We know that during the reaction, chemical potential energy within those chemicals is transformed into heat energy to the system, and we can measure that using the formula Q equals mc delta T, how much heat was, released into the system. So, and because of the first law, we know that chemical potential energy that was stored in the bonds, which is what delta H is a measure, which essentially that is what delta H is, that chemical potential energy stored within the bonds. We know that the only conversion it could go to is thermal energy, and then the reason it's because of the reason we divide it by the moles of the limiting reagent is because the limiting reagent controls how far the reaction goes. So therefore, obviously, if there's a limiting reagent, if one react as an excess and some other bit of it is limiting, obviously not all the reactant reacts, only some of it reacts, and it'll only react according to the limiting reagent moles. And you can check this dimensionally that it works. We get that Q we can measure in kilojoules, and moles we measure in mole, and therefore the units work out as well. So that's the reason why that formula works, and we're going to use that fact. And the negative there is just to indicate that is just there to indicate for conservation laws that the first law that the magnitude of this change is equal to that, but since they're opposite, since we gained this and we lost this, we slap a negative sign on there. Alternatively, we could have just put that, but that's not. We typically write it with negative to indicate that. So that being said, now we can go back to so we can start by just calculating first what is the limiting reagent. So where's my mouse? Okay, here it is. Now we know that the reaction that they give us, the neutralization reaction, is HCl plus NaOH. I'm going to find the limiting reagent first, just so that we know what this denominator here becomes NaCl plus H2O. And we can do our little chart here. Before, after, and we are told that that's 51 2 molar 1 1 1 1, and then we know this is 50, but also 2 molar. So straight away we can see here that since these concentrations are the same, the volume is proportional to the number of moles, because in this case, since we're working with liquid solutions, we know that N equals C times V, or alternatively, well, we know that N equals C times V, and so therefore we know if this goes up, and this is held constant, this has to go up as well. So, um, so because of that, I can straight away deduce that this NaOH is the limiting reagent. So I'll just put a little L there to indicate that that's our limiting reagent. So now that that's done, and we can start to form some of this, we can start to calculate things. So now the next thing I want to calculate is delta T, because I know that m times c times delta T is the formula, so we can write this as negative m times c times delta T over n lim. Just now, let me switch back here to to the graph. Now, we know that we have to guesstimate our initial temperature, so we can guess that now we our initial temperature looks to be at about, so if that's 26, that's 27. That looks to be about a third the way there. Let's call it 26.3. So you know that T I equals 26.3 degrees Celsius. TF we know is, well, we're going to find that later. M equals just the mass of those two solutions together, and you can assume that the density is 1 gram per milliliter. So we know that the total volume of the solution, since we have to add the volumes of the two solutions and then use the density to convert. The reason we add the two solutions there is because it's the mass of both of them that is absorbing the heat. It's not just one or the other. So 51.2 plus 50, that's what's absorbing all the heat that is released by the reaction. So that is, no, not 51.2, 51 plus 50, which is 101 mils. And then I know the density of water is 1 gram per 1 mil, which is, so the mass is 101 grams. C I'm given is 4.18 joule Kelvin gram negative 1. Yep. And then lastly, the final temperature, if we go back to our graph here. Now, you would be forgiven for saying that, okay, here's where about the final temperature is, and that looks to be about, I would say 32.8. You'd be forgiven for using 32.8 as your final temperature. However, that's actually wrong, because note that through this entire process, heat is always being lost, right? Because that's the way heat loss works, that the greater the, heat is always being lost to the environment. So if you heat something up, it's going to naturally dissipate into the environment somehow. And the way we account for that in our experiment is, you see this part here where it starts to, cool down. There's a cooling down rate. Now, we essentially, assuming the same rate of cooling, we can extrapolate this data. So we can draw like a line with, typically you would use a ruler. I can't do that in Word. I don't think so anyway. So I'm going to trace my mouse following that line, and using that I get an extrapolated temperature of about, what is that, 33.1? Yeah, 33.1. Let's call it that. So using that, we would call it 33.1 degrees centigrade. And again, that's just me extrapolating the data. And the reason we extrapolate it is because there's always heat loss in the environment throughout the entire process. So in order to try and combat that, we assume that, okay, it's going to cool at the same rate. And if we make that assumption, we can sort of estimate where the final temperature would have been had heat loss not occurred, more or less. And now that we have all our data, it's pretty actually straightforward to calculate it. So I'll calculate it. So we get the expression as negative 101 times 4.18 times, so remember, Temperature difference is always final minus initial, so 33.1. Subtract 26.3 over 50 milliliters. And I know that there's 2 mole for every 1,000 milliliters. And then if I do the math on my calculator, which I'll do right now, that works out to be and I get the answer is negative 28.7 kilojoules. Now I actually get 20 minus 28,700 and something else. Um, yeah, I get like, you know, I get like 28,700 and whatever. But remember, that's in joules per mole, and we want to convert to kilojoules, so just divide it by 1,000, and you get the enthalpy change of reaction is that. Now, the accepted value of this delta H, according to theoretical calculations, is about, double that. Now, why is there error in our? Why are we off by that much? Now, the biggest reason is just heat loss. We There's just a lot of heat loss in the mixture as a result in the calorimeter, and I suppose one way you could reduce the error by just using less concentrated solutions or bigger volumes, because delta T, if you use small volumes, if you use if you cause delta T to be greater, there's less sort of error in your measurements since there's more heat being released that you can measure. Um, Another way, you could just use a bomb calorimeter and not a coffee cup calorimeter. And yeah, now this generally doesn't have much real world application. You'll generally be finding enthalpy changes other ways using, formation or bond energies. However, typically this is actually a common prescribed practical, this more or less exact practical. So I do it for more because it's a common practical, and I think you should be familiar with how it works. And with that, thank you for watching. Don't forget to like and subscribe.